Here we will work on a few problems involving electron movement arrows. We will see a few things here that make the problem look more complicated, but we will also see how to deal with them. These problems will all be one mechanism step. In one, you will be given the reactants and the electron movement arrows and asked to write the products. In the other, you will be given the reactants and the products and asked to write the arrows. All of these mechanisms will involve moving electrons in pairs rather than individually. These problems do not require knowledge of organic chemical reactions. So go for it! First, I've listed here for you a quick review of the key concepts that will be needed in solving the problems. These are also available as a downloadable handout. Number 1. Arrows point from the electron pair that will be moved to its new location. There are a few judgments additionally that you may have to make here. A. If a bond is broken, the atom at one end will stay connected to the electrons and perhaps use that pair to make another bond somewhere. It may be obvious which atom of the bond stays connected to the electrons and which atom loses them, but in cases where it isn't obvious, generally the atom that stays connected with the pair is the atom from the bond that least wants to lose electrons and become plus. In some cases, there is a mixture of products because either of the atoms from the bond could react. Relative stability of cations will be mentioned throughout your study of organic chemistry. B. Since an arrow pointing to an atom means either that the electron pair goes onto that atom as an unshared pair, or, more commonly, the electron pair makes a bond to that atom. Since the situation of getting an unshared pair can only happen if the breaking bond is already attached to that atom, the decision as to which process is meant should be easy. 2. Always write the proper formal charges on any structure you draw. The atom that lost the electron pair gets a formal charge +1 higher than before, and the atom that gained the electron pair gets a formal charge with 1 more minus. Here are the problems. Pause the video and give them a try before moving on to the solutions. These are also available as a downloadable handout. Problem 1. Write the product of the reaction mechanism steps shown. Okay, the first thing to say to yourself is, it doesn't matter if I've never seen this problem before. I can figure it out. The second thing you say is follow the rules. I have the rules listed up on the top. The first is that arrows always point from the electron pair that will be moved, that's this pair, to its new location. Now the new location either gets that pair of electrons as a lone pair, or it gets a bond from one of the atoms. Now it only gets an electron pair if the bond being broken is the one that is attached to that atom. In this case, therefore, we are getting a new bond formed. When you break a bond, you have to think about which end of the bond is going to connect to the new atom and which one is going to lose its electrons. In this case, I think you can probably guess the O will connect to the C. We'll talk a little more about that in a minute. Okay, so we have here a structure. We understand what's going to happen. We need to draw the product. I think it's easiest if we start out drawing what we had at the beginning, and especially if it's a complicated molecule, and then take an eraser and do what the arrows tell us to do. So here we're going to get rid of this bond, and then we're going to make a new bond between the O and the C. Now the second step here is that we have to check our formal charges. The atom that lost the electron pair, that's in the bond over here, that one lost the electron pair. That becomes plus 1 more than it was before. And the atom that gained the electron pair, that's the C of the CH2, gained a minus 1 because it gained an electron, so that ends up making it neutral. So there we have our product. So we're actually finished. But I like to write my ring compounds in nice geometric structure. This is kind of messy, so we'll make our structure a little neater. We have here a 6-membered ring, if you count the atoms, and we're going to take the plus charge and put it on the second position away from the oxygen, counting around. So there we have it. Now, one thing you might want to consider is, and we'll just look at this as an exercise, even though it's probably obvious, that you might have had the other end of the bond, this C, being used to make the new connection. But now that I said that, you can see immediately that if we were to make our new bond between that carbon and the CH2, we'd have a double bond there. And that is not what the diagram says. If the diagram meant that, it would have had the arrow going to the bond to make a double bond. Now the reason it doesn't happen that way, besides the fact the arrow didn't tell us, is that the atom that is going to become plus in that situation would be the very electronegative oxygen atom. And oxygen likes even less than carbon to have only 6 electrons around it. So our actual answer is going to be the one we drew. That's this. Problem 2. This one is a different type. Instead of writing the product given the arrows, we need to write the arrows given the product. So this will be solved in a somewhat backwards way from the first problem. Okay, so this one really looks a mess. Remember the first thing you say, I can figure it out. We need to start with some logic. Since we're going to write arrows to describe the change, we need to clearly identify what that change is. What is different between these two pictures? We can easily cross off what is the same. Okay, phosphate group, same. CH2 same, CH2 same. That carbon's different and the H is the same. The N is different bonding. This is the same. Double, single, the OH is the same. The benzene ring is the same. Okay, I think we have it. Now what we need to do also is to identify, I'll just circle this, the piece that changes. That, this, and this. Another thing that is useful to do, in fact it's very important to do, or you might make mistakes, this structure is written in condensed format. So it's really a good idea to add in the lone pairs of electrons and the missing H's. Okay, so we have a lone pair there, 2 lone pairs here, no lone pair on that nitrogen, 2 H's, and 3 lone pairs on the oxygen. That's the anion. Okay, I'm just going to write you a note here. Write lone pairs and hidden missing H's. Now, let's look at what changed very carefully. At the bottom here, we see that there's an OH on the left and an O minus on the right. Since the O became minus, the bonding pair between the O and the H must have gone to the O. Let's draw out the OH bond here so we can see it, because we're going to have to be looking at the bonding pair and what happens to it. So we'll write out the OH bond and we'll draw in our first arrow. Since it becomes O minus, we must have the electron pair going from there to the O. One arrow done. But where is that H going in the final product? Look around. We added an H right here. So we're going to be putting that H on from the OH in the original phenol compound, the aromatic OH compound at the bottom. All right, how does it get there? A pair of electrons is needed to bond to that H, since it is removed from OH without its electron pair. So the double bond is bonded to the carbon where you have the connection. The double bond could use its pair of electrons to bond to that H. That would connect it to the place it's shown. Now what about the other double bond over here on the final product next to the N? Where did it come from? It came from the lone pair on the nitrogen. If you hadn't written that lone pair on the nitrogen, do you think you might have come up with something like this? I'm going to redraw my original structure and then put in something that somebody might have thought of. Okay, now if I hadn't drawn in the pair, I might be tempted to go here to there and then here to there. Okay, what's wrong with that? Well, for one thing, the nitrogen here actually has 10 electrons around it. That is not good. Nitrogen can't have 10 around it and can't have more than an octet. And you did the unthinkable of using an electron pair moving arrow to show the movement of H plus that has no electron pairs on it at all. So overall, this is a really lousy answer. And you would get that if you hadn't written the lone pairs, or at least you'd be more tempted to do that if you hadn't written the lone pairs. The two problems we have just done, while being challenging examples, were only one mechanism step, and you were either given the reactants and arrows and asked to write the products, or the reactants and products and asked to write the arrows. Figuring these problems out involved mostly looking carefully and following electron movement arrow rules, not knowledge of specific chemistry. As you study more chemistry, you will learn how different functional groups tend to react. For example, a C double bond C tends to use its pi electron pair to make a bond to another atom. At that time, you will be asked to write both the arrows and the products given only the reactants.